Thank you. I'm very excited to be here in Australia, coming here from Portland, Oregon. I think we're a hard case, so it'll be good to see what you guys think as we talk about this. I'm going to talk about two projects today. One, which is Framework, which is currently the sort of the first high-rise permitted building in the United States and in North America. And also, it was also the winner of the U.S. Tallwood Building Competition, which was a $1.5 million grant to actually allow for a building to be built via performance-based design that doesn't currently exist in the code. The other project I'm going to talk about is our office, which is a CLT building. It's 4 stories, so probably one of the shorter buildings that will be talked about today. But it's the first building using domestically fabricated CLT, and what I mean by domestic, US fabricated CLT in the United States. So it was in its way a very interesting building. We learned a lot, and both these projects are kind of like a big brother, little sister. But there's also, I think, as we talk about wood, I think we have to kind of back up a bit and talk about the culture of wood building, at least how it sort of evolved in the United States. So this is, in a way, our holy grail of wood, which is timber frame construction, which was actually first introduced in the United States, balloon frame in 1840, and we spent the last almost 200 years perfecting it, making it more efficient, making it cheaper, making it faster. And that's really what we have to compete against in the United States, because we build many buildings out of that type of building, and so it's a bigger issue for us. This is an important image for me. This is some of the last CLT panels being placed on our office building in Portland, Oregon. And it combines something that's also important to us, is this idea of CLT as something that connects the explosive growth that we're seeing in our urban environments to rural economic development, to forestry management, to jobs. A place like Oregon, where I'm from, in the Northwest of the United States, we have a big disconnect from what's happening in our cities to what's happening in our rural economic communities. And this is really connecting, basically what you see here is the range that all this wood comes from. So there's a direct connection between those two pieces. This is the space we work in. We're and the top floor of our office, which is, you can see it's a little different. It's a dug fir CLT building. As a practice, we're very interested in how we can rethink the way we build to create great experiences. And one of the things that is so exciting about mass timber is an opportunity for architects to get almost into I almost call it the bones of the building, really understanding the detailing and how that goes together to create experiences that connect our buildings to our landscapes. And this is Portland, Oregon. This is our volcanic mountain, Mount Hood, which really defines our landscape. It's funny, I was in Melbourne 2 days ago, and it reminded me a lot of Portland. It's a city that is very young, really from the 1850s on. It's very, in a way, defined, like Australia, like very much by the landscape around it. One of the things that got me interested in architecture and interested in wood initially was our connection to it, the idea of the experience of being in an all-wood building. This is actually a house that my great-grandfather built in 1928. In Cape Cod. And this is a house where you can really see the experience of how it was put together. You can actually see the fingerprints of the carpenters, 2 Irish carpenters that put this together. And I only found out about maybe a couple of years ago that it was actually Oregon pine that was shipped from the west coast of the United States by rail. My great-grandfather bought a boxcar and then put that together. A couple other projects that are important is this retail passageway, which is where we kind of developed this idea of what we call forest to frame. It's kind of a play on farm to table. So all the wood you see in here comes from a forest that is a FSC certified forest 3 hours outside of Oregon. It's farmed forestry, but we were able to kind of go directly to the owner of the forest, schedule the harvest of that wood, have it machined in Portland, and then installed into this sort of small retail passageway. And that really kind of connected us to this idea that the materials we use to build buildings, sort of like the food that we purchase to kind of create a great meal, that we can be connected to that as architects. We can think about the impacts of what we choose to build with into how we think about buildings. This is another project that's in Los Angeles. It's for a entertainment company. It's a different way of thinking about materials. So the same distance, say, from that previous project to the forest, which is about 2.5 hours, is really kind of connected to this, because in this case, we actually salvaged wood from within Los Angeles. So all the wood you see here was salvaged from a gymnasium that was being torn down, and we actually reclaimed it to put it into that building. And that's sort of the effect and the experience of the wood within that structure. So what does this have to do with tall wood buildings? I think for us, it's about a little bit of a journey of understanding how our culture relative to wood in the Northwest has translated into the buildings that I'll show you recently. So most of the type construction you see here is actually utilize what's called a 5/1 construction type, which is basically a floor of post-tension concrete and 5 floors of stick frame construction, which is what you saw on that initial slide. And we've taken that kind of culture of building with smaller timber and developed it to its extreme in a seismic zone. So this is high seismic zone. This is an 85-foot tall structure in the back. First 2 are concrete and the upper 5 are stick frame. So that kind of culture, that sort of understanding of how to build is an important part of what we do. And this building is actually a direct outgrowth of some of the commodity products that we put into these 5/1s. The glulam beams you see here are all prefabricated about 3 hours south in Southern Oregon. Oregon is the largest producer of timber products in the United States. We have about 800 million board feet per year. I think it's almost 1 billion. I think about 800 of that is shipped overseas, probably some to Australia. But this is a winery where we're using a commodity glulam product to create the experience. And that's something that we keep coming back to when we think about our architecture. So building tall with cross-laminated timber. Albina Yard was a kind of exercise in really trying to kind of build a supply chain. Because when we started this project, there was no domestically available CLT in the United States. So we were working directly with the manufacturer to sort of understand how we could actually create that building. So we were kind of designing 2 things at once. And we weren't just interested in using CLT, we're interested in what is the architecture of CLT relative to the material properties of that material. One thing that's amazing about CLT is that you can cantilever quite a distance with a very thin dimension. So I'll just say it's around 4 inches, which is 3-ply CLT. We can cantilever 4 feet, which is about slightly 1.5 meters. And that's really what the expression of this building is this is a commercial office building. There's no grants, there's no support. It had to actually stand on its own, but we were interested in that expression being the sort of simple move that creates the building. This is the actual press that all the CLT that was in this building was manufactured on. And in order to actually make this building happen, we really worked on starting with the actual dimensions of the press, which is 10 feet by 25 feet, and using that to determine the module layout of the building. It's a little different than starting with the most optimized layout for office. It was really saying, how can we be the most efficient in using this material to actually make it happen? So this is actually 1 floor arriving on site. So it left Southern Oregon at 6 a.m., arrived on our site at 9 a.m., and by around 1 p.m., we placed 4,000 square feet of flooring. So that's around 400 square meters. So you just sort of see, the speed that these go up with, how quiet it is. I think it's sort of just, there's not a lot that needs to be explained here. You can sort of see how these are maximizing the panel dimensions themselves. So we're cutting them, basically as little as possible. And after this building was complete, we basically were able to convince the manufacturer to invest in digital fabrication for those panels. So this is sort of the neighborhood we're at, and I'll just move on from here, but you get the basics. One kind of key thing with wood is, what do you do in rain? Well, it rained the entire time we built this frame. And I think that's important to understand. That is a key piece of the equation, really managing water and understanding how to do that. You see how all the connections are white? It's because they're powder coated so they don't stain the wood. So those are some kind of key things that you need to understand as you're building. And this is the interior of that space. our main conference room. Like Philip was saying, we're just exposing the utilities. It's very straightforward and simple. We're using a glue-laminated glazing system that's actually also made in Oregon. Actually came out of beach houses and greenhouses that were built in the 60s, and they've been around since that time. Now they're updating their systems to some of the things that we're doing. This is the back stair showing the CLT with the 3-ply panels. You see that 3-ply panel is the exact same structure that we're using for all the floors on the glulam structure. And this is how these things were actually cut. I think it's important to sort of understand the kind of process. This was the first time that we're aware of that domestic product was actually cut using CNC, because we had this Hundiger machine that was actually available to us. They were using it for truss manufacture, and we were able to actually use it to cut these dreams. All of the connections in this building were designed specifically to resist the seismic drift requirements that we actually had to accommodate. So that's the thing in the United States that we're really dealing with now, is, at least on the West Coast, is the seismic. It's a big part of it. A lot of the European connectors weren't necessarily expressly designed for that type of construction. So that's something that we're dealing with. We're dealing with this on this project, and this was a great warm-up for framework. So this is the connection system that we developed, all fabricated in Oregon. And I wouldn't necessarily do this exactly the same way again, but sometimes you have to make your own mistakes to get to the next level. But part of the interest with this project was really to think about how could we really encase very strong steel connectors within a wood component. So this is how that looked, detailing of it. And yes. And then we have, if you do come to Portland, Oregon, we have a nice little bar in the back. And we threw in some containers on this project just to make it a little more difficult. So I'm going to end with framework, and I don't know how much time I have left. 14 minutes, okay, so that's good to know. Framework is something completely different. It's basically building a building that doesn't currently exist in the code in the United States. So once you get above that magical 85 feet, you're basically out of anything that's prescriptive. So what we had to do was actually really put together a performance-based design with the authorities having jurisdiction, which in this case are the state of Oregon and the city of Portland, and create sort of a step-by-step path that's proved out through full-scale testing of components, also nonlinear analysis of the structure, both fire testing, acoustic testing, seismic testing, and we were also exploring a resilient design. We were thinking, what can wood do that maybe other materials can't maybe do as well, because wood has a very high strength-to-weight ratio, and I'll talk in detail about sort of what we did. But I like this image just because it really shows you sort of the red line. Getting above this line, at least in North America, is really challenging right now because we have to go with a performance-based design piece. And then I think the most important thing is thinking about the actual material you're using. This is an old growth Douglas fir, 260, 300 feet. These living structures are higher than any high rise that's actually being contemplated out there. So that's something that's important to think about as well. When I talk about CLT, I also want to talk about what it's not, because I think people think you're going to be cutting down old growth forests. Well, we're actually not. This is what we used to cut down in Portland. These trees still exist, actually, in some parts of Oregon. So this is in our institutional memory, in that most of our big warehouse buildings are made with these really old growth timber. And you can see one here on the right that's actually owned by EcoTrust, which is an environmental organization, but they're actually getting involved in timber as well. But I think we're doing the opposite. We're really looking at timber at almost I would say, a molecular level, and in some cases even smaller, to really understand, what wood can do. And I think this illustration is a good kind of illustration of wood is this sort of fibrous structure. And if you think of it like a series of straws, It's very strong just in that perpendicular to the grain, on the end grain, but it can move and absorb water perpendicular to the grain. And what CLT does is really take those two sort of characteristics and laminates them together to create a very stable panel. And that's really the revolution of CLT. It was the revolution of plywood many years ago, and I think that's why people are really excited about it. I think Philip talked really well about this idea of sequestering carbon. The big thing for us in, I would say, not only Oregon, but in the United States as a whole, is this idea of rural economic development and connecting sort of the development of this building type to the well-being of our communities that are actually situated where the timber is grown. So we're really thinking of ways that we can actually stimulate that so that those people can actually be part of the explosive urban growth that's happening in our cities. And this illustration on the left really talks about that as a big part of this movement. Some of the key things about the framework, we have a permit. So it will be the first permitted high-rise building in the US. We're starting construction this winter. It would be the tallest all-mass timber building in North America. And, you know, I think you can debate that. I mean, what we are doing is we're using a different type of lateral system, which is a post-tension rocking wall system. So what it is basically, if this is a shear wall, it's basically tensioned down the center with 4 rods that are about 1.5 inches in diameter. And those rods actually allow the building to self-center in a major earthquake. So structural engineers understand that. So that's really the sort of innovative issue that we're looking at with this project, and I'll talk about it more. The other key things we've done is we want to expose the wood. So we've carried out over, I would say, 40 full-scale compartment tests of particular combinations, including the first successful 2-hour fire-rated beam, column, and CLT test. And I'll talk a little bit about that. This is the main structure of the building. So we have these 8 post-tension cross-laminated timber rocking walls. We have the frame, which is a gravity frame, doesn't take any lateral. And then we have sort of the branch canopy of the CLT panels. This is sort of, to understand, this is some of the nonlinear analysis we've done. This is very exaggerated, it doesn't move that much. It's just so we can actually see the movement. And then this is sort of a good diagram, a model of how that structure works. The post-tensioning works like, walls work like this. You can sort of see here, oops, go back a bit. You can see here, there's a series of what we call UFPs, which are U-shaped flexural plates that actually connect the CLT shear walls to the gravity frame. And they can actually, in a major earthquake, they can actually deform and they slow down the acceleration of the building, and then the post-tensioning pulls it back to center. We're also involved with an NSF-funded grant to test these systems full scale. So this happened about about a month ago in San Diego. So basically, you're going through a major earthquake here. We took it through, like, I guess, 10,000 years of earthquakes in a couple hours. But that's the sort of UFP that you see here. This is the post-tensioning on these walls. In about 1.5 years, we're going to be doing a 10-story version of this and on the same shake table, and then we're going to burn it down. So going back to just the idea of the initial design, if you saw that image of this old growth tree, we really wanted to express this building as a wood core, and that would be visible at the urban street level. So these rocking walls you see here are visible. There are also heat recovery systems on that facade. And we have basically retail on the ground floor, 5 floors of creative office, and then 5 floors of affordable housing. So we have a lot of different entities that are involved in this project. Both one of the developers we're working with project, they basically say it's almost like 3 projects. There's a research and development project. There's basically a for-profit commercial office project. And then we also have this affordable housing component that's connected to the bank. That's actually being funded by the city. So this is the sort of office component floors. These are the affordable housing. And you can see in these levels, we're actually only exposing the CLT on the ceiling. And then this is the sort of facade, which is a simple sort of folded element that is in a way inspired by the fact that, at least in a place like in Oregon, where we have the forests, so it's like the color changes based on the geometry of the buds as they open from a yellow to green. We wanted a building that really changed in the light, and these are some of the mock-ups that we have. We don't have that much light in Portland except in the summer, so this is an important part of the design. So I'm going to end talking about testing, and maybe we have time for some of the new technologies. These are the test blanks we used for the seismic testing for the rocking wall system. This is the actual test. So this is taking that rocking wall that I talked to you previously, and it's putting on its side, and then basically that's the post-tensioning, and we're putting 500 kips of pressure to test the connectors. What we needed those walls to be is incredibly stiff. This is sort of the opposite of this. This is the actual perimeter beam connection, where we're actually testing the drift. You know, we needed to get 2% drift for these connections, and this actual connection, which is a spring-loaded perimeter connection, actually went to 6% with almost no damage. This is the acoustic testing we did in Intertech in Pennsylvania. Arup was involved in this, actually, on the acoustic side, and also in the fire engineering. And the engineering of the rocking wall was done by a local Portland firm. It's a West Coast firm called KPFF. So fire, everyone says, you know, this is in a way, and I think this came out of the conference we talked about, is this is one of the bigger challenges with wood. I think one of the key things to understand with wood is that massive wood has inherent fire resistance. Doesn't mean it's not going to burn, but the charring that happens in massive wood actually slows the heating of the interior of the wood. And if you think of it this way, if you have a fire in your fireplace, if you have one, sometimes that big log just doesn't burn. It just goes out. And then if you try to light that log the next day, it's very difficult. You almost have to get a roaring fire. So that's a good illustration of sort of the charring that happens. So one of the things that we really wanted to do in this project is we wanted to expose some of this wood in this building. And I think the key thing we learned and we're engineering is how much wood could we expose, because wood contributes to the fire load of buildings. So you have to really understand that energy and accommodate it in your design. Just like if you're designing a bridge, you need to accommodate and understand what kind of traffic you're going to get on that bridge and what is the safety factor. So that's something that we're really working on in this. This is the actual connection detail that was tested and went through the 2-hour fire test. You can see here that we have very little steel, and it's basically buried within the wood structure, so that it can actually burn without heating that steel in it. And this is the testing that was done in Texas. So I'm just gonna run through this little video. So this is a 2-hour test sped up, and you can see, take a look at the little monitor up there. You'll see here, that's the column, this is the beam, and as the fire gets hotter, you might be able to see it's a little hard in this view to see it. But you can sort of see it there. That's that beam right there, and then you start to see the fire starting to come out. This is actually a fully loaded test, so every test that we do has to also have the loading. So there's not as many labs that can actually do that type of work. And this is what it looks like when it comes out. So that's after 2 hours, still fully intact structure. So since I have 3 minutes left, next generation, we're very interested in not just CLT, but what new products, new ways of thinking about wood will coming out there. And this is a project that we just finished. It's called a mass plywood pavilion, which is using technology is relatively new in the United States, where we're actually making massive plywood. So it's not just plywood laminated together, it's basically structurally perfed together and then laminated into major panels. And this was just a simple kind of project, and I'm going to run through this video. This is a veneer plant in outside of Portland, Oregon, about an hour and a half away from the city. This is how plywood is manufactured. You can see why plywood is so efficient, because unlike, say, CLT, you're basically unrolling these logs. And this is actually the fabrication of that particular material. These were their first sort of 17 by 4 foot panels. You can sort of see the cantilevers on those are almost like 4 meters. This material, we believe, is about 30% stiffer than CLT. It's a lot harder, and it's actually, in terms of its use of fiber, more efficient. It has more glue, so that's also an issue, so that makes it harder to machine. But I think I wanted to show this. This was actually assembled in 1 hour at the Portland Art Museum. I wanted to show this because I think you can focus on one material, something like CLT, and you're not really sort of looking ahead to what's next. So I think, just to close, I think one of the key things, quotes that I like to use is, it's from Leonardo da Vinci. He says, "Think well to the end, begin with the end in mind." And I think that that's very important as you think about working in a new technology. You can't just be thinking about the design, you need to be thinking about the entire supply chain. And appreciate you guys listening. Thank you.